Okay, on example 7, pause the video if you would and take a minute to read example 7. We're going to find gallons of, I don't know what we're pumping, gallons of something that were pumped. Let's see, a pump connected to a generator, depending on how much power is being drawn. Gallons per minute which the pump operates is recorded at 5-minute intervals. So we don't have continuous data here. We have a set of data that tells us every 5 minutes the rate at which the pump is pumping whatever it is that it's pumping. So if you think about graphing that data, right, at time 0, it's pumping at 58 gallons a minute. At time 5, it's at 60. At time 10, it's at 65. You end up with some sort of a graph that you could find the area underneath of, right? So you could find the area, right, of each one of these shapes, which ends up being trapezoids. So this is sort of the integral that we want to find, but we're going to use the trapezoid rule to do an estimate of that. And that's the best we can do when we have data like this. So if you think about the width of each of these pieces in the trapezoid, that this first trapezoid is going to have a width of, each of them is going to have a width of 5. The height of this first trapezoid is 58, right? And then the height of the other base of the trapezoid is 60, but then remember that 60 is going to get used in the second trapezoid. So what ends up happening when you use the trapezoid rule is that the very first number in your data and the very last number in your data only get used singly, but all of the numbers in between end up getting multiplied by 2. Right, so I'm going to think about this trapezoid. That trapezoid has base 1 of 58 plus base 2 of 60. So remember that it's base 1 plus base 2 times the height, which is 5, divided by 2. And then the next one is going to be 60 plus 65 times 5 divided by 2, and so on. Right? If you look at what they did here, they kind of did two things. This 60 divided by 12 is my 5. Right? They said, look, this interval has a length of 60, and there are 12 subintervals in it. That's why they did 60 divided by 12. And then this 2 is just this divided by 2 factored out. All right. So another way that you could think of this at the front is just the width of the interval and then that divided by 2. And then what ends up happening is that you've got that first height once, and then all the in-between heights times 2, and then that last height. And that gives you the estimate of how much was pumped during that hour. All right, sorry about that. The last example, but in this case we know. Okay, the last example that we want to do has to do with work. So pause the video here and take a minute to read this part. And know that in math, what we're concerned with is that force is equal to a constant, K. All right, what happened? All right, sorry about that. OneNote keeps disappearing on me. All right, so using Hooke's law and just looking at the math of it, force is equal to a constant K times X. Okay, so the force it takes to stretch or compress a spring X units from its unstressed length is a constant K times X, and X is the number of units we want to move it. All right, so if we look at this example, it says that it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length, right? So it takes 10 newtons to stretch it 2 units, right? So that's that force is equal to the constant K times the number of units. And so we can figure out that K is equal to 5. And so our force equation is that the force that it takes it to move it X units is equal to 5 times X. Okay? So the question says how much work is done in stretching the spring 4 meters from its natural length. And so the important part of this, the thing that you need to know, is that work is the integral of force. So if you look at the setup down here, that's exactly what they did. So we want it to stretch 4 units. So we're going to take the integral from 0 to 4 of that equation we just found out, which was 5x. So if we take the antiderivative of that, we get 5x squared over 2. And we want to evaluate it from 0 to 4, which is really simple math. That ends up being 4 newtons times meters, which I think is a unit called a joule. But that's a question you could actually ask Brad. This kind of a work question is not nearly as complicated as it seems when you first look at it. You just have to find that force constant and then the integral of force's work.